Hello everyone, I am Asha, Assistant Professor in Artificial Intelligence and Data Science. So welcome to this video series on data mining and data warehousing, where we will learn how large amount of data are stored, organized and converted into useful knowledge. This series is designed especially for ADS students with simple explanations, real-time examples and exam-oriented coverage. Let us start our journey of turning data into insights. Cluster analysis is a data mining technique used to group similar objects into clusters based on their inherent characteristics. In simpler terms, imagine you have a room full of people. Cluster analysis is like asking everyone who likes cricket to stand in one corner, everyone who likes movie in another, and so on. So the algorithm automatically finds those groups for you without you telling it in advance what the groups should be. For example, a school librarian clusters books into fiction, non-fiction, science, history, etc. No one told the librarian where each book belongs in advance. She figured it out by looking at the content. So cluster analysis does exactly this, but with data. Okay? So before clustering, your data looks like a random scatter of dots on a page. After clustering, those dots are organized into neat groups like colored bubbles. The algorithm does this automatically by measuring how close or similar two data points are to each other. Why do we need cluster analysis? 4 core reasons for that. Discover hidden patterns. Organize large data sets. Identify natural groupings. Support decision making. So discover hidden patterns means like imagine a hospital with thousands of patient records. Just looking at numbers won't tell you which patient have similar health conditions. Cluster analysis automatically uncovers the relationships and patterns that are not immediately obvious to the human eye. Okay? So this is discovering the hidden pattern. Raw data rarely reveals its secrets directly. Second one, organize large data set. In the age of big data, we deal with millions of records daily. Cluster analysis helps transform overwhelming volumes of information into smaller, manageable groups. Instead of analyzing 1 million records one by one, you analyze 5 to 10 clusters, each representing a group of similar records. Okay, third reason, identify natural groupings. That means data often has natural segments that exist within it. Cluster analysis finds these meaningful groups automatically. For example, customer purchasing behavior may naturally form groups. Budget shoppers, premium buyers, occasional shoppers, like that. Okay? And the last one, support decision making. Once clusters are identified, businesses and organizations can take targeted actions for each group. A hospital can provide specialist care. A company can run targeted marketing campaigns. A government can allocate resources to specific zones. Okay? I can give you a real world example. Netflix. Netflix uses cluster analysis to group its millions of viewers based on viewing habit. Action lovers, comedy fans, documentary watchers, etc. So when you open Netflix, it already knows which group you belong to and recommends the content that other people in your cluster loved. This is why Netflix recommendation feels so personalized. Okay, so can you think of two more real world applications where cluster analysis would be useful? Think about e-commerce, healthcare, and social media. Next, types of data in cluster analysis. Before we can cluster the data, we need to understand what type of data we are working with. Different data types require different similarity measures and different algorithms. So there are 5 main types. First one is interval scaled data, that is numeric data, where the difference between values is meaningful. Example, temperature. The temperature was 20 degrees Celsius yesterday and today it is 25 degrees Celsius. Then what is the difference? It's 5 degrees Celsius. That is meaningful. Age. 5 years back I was 25. Now I am 30. After 5 years I will be 35. So these values can be added, subtracted, compared directly. Most common in scientific measurements. Okay. So second one is binary data. Data that can only take one of two possible values, yes or no, true or false, male, female, encoded as 0 or 1, disease, present or absent. So binary data is in the simplest form. Similarity is measured by how many attributes match between two objects. Okay, third data type, nominal data. Like you can categorize without any inherent order or ranking. For example, colors. I can group them like red, blue, green. Country, India, USA, UK. Blood group, A, B, AB, O. So there is no sense in saying like red is greater than blue or red is dull than blue, red is dominant. No, these are just labels. Similarity is checked by matching or the values the same or different. So this is nominal. Next one is ordinal data. So categorized with a meaningful order, but the exact difference between values is not defined. For example, education level. High school is less than bachelor. Bachelor is less than master's. Master is less than PhD. Survey rating. Poor less than average. Average is less than good. Good is less than excellent. Competition ranks, first, second, third. So the order matters, but we cannot say good is exactly 2x better than poor. We cannot say. Next one is ratio data. See, numeric data with a true 0 point. Numeric data with a true 0 point. 0 means nothing. Example, weight 0 kg means no weight. Salary 0 means no income. Height 0. 0 means no height. Unlike interval data, ratio are meaningful here. Okay. So I can say 50,000, 50k. That is also 0. So if I want to conclude, like if I want to give summary for this, I'll say binary means what? Two values. Nominal, only the names. Ordinal, order matters. Then interval, difference matters. Ratio, it has true 0. Remember it as BNOIR, like the French word for black. Properties of good clusters. Not every grouping algorithm produces useful clusters. A good clustering result must satisfy certain properties. Think of it like grading a solution. How do we know our cluster are actually good? So, high intra-cluster similarity. See, objects within the same cluster should be highly similar. If you have a cluster of action movie fans, everyone in the cluster should actually love action movies. If some people in it prefer romantic comedies, then the cluster is not pure. It has a low intra-cluster similarity. Okay? So, low inter-cluster similarity. Objects in different clusters should be clearly different from each other. The cluster of action fan and the cluster of romantic fans should be different. If they overlap heavily, the clustering is poor. We have not clearly separate the groups. It's highly impossible. Okay, next, computational efficiency. The clustering algorithm should process the data quickly and use memory and computing resources wisely. An algorithm that takes 3 weeks to cluster a data set is not practically useful, even if the clusters are perfect. So, we need a clustering algorithm which should process the data quickly, fast. Next one, scalability. The method must handle large data set effectively. A clustering algorithm that works perfectly for 1,000 records but crashes or becomes extremely slow within 1 million records. So that will lack scalability, right? So good algorithms must scale gracefully. So these 4 properties ensure clusters are meaningful, interpretable, and useful for analysis. So think of them as a quality criteria for clustering, just like how you evaluate the quality of a model in ML using accuracy, precision, and recall. You just look at the slide diagram. Good clustering shows tight, well-separated circles. Poor clustering shows scattered, overlapping dots. So this visual comparison is the easiest way to understand intra and inter-cluster similarity. Clustering scalability. So scalability refers to a clustering algorithm's ability to efficiently process very large data sets while maintaining performance. This is one of the biggest practical challenge in real-world data mining. Why is scalability a challenge? Millions of data records. Modern databases can have billions of entries. An algorithm that works on 10,000 samples must be impractical on 100 million. High dimensional data spaces. A customer might be described by 500 plus attributes: purchase history, demographics, browsing behavior, etc. So high dimensions increase computational complexity. Processing time constraints. Businesses need results in hours or minutes, not days or weeks. Memory limitations. Large datasets may not fit in RAM, requiring algorithms that can process data in batches. So this is why the scalability is a challenge. So how do we measure the scalability? We use big O notation to express how an algorithm's time or memory requirement grows with data size. For example, O of n, linear time. If data doubles, time doubles. Excellent scalability. O of n square, quadratic time. If data doubles, time quadruples. Poor scalability for large data set. O of nkt. K means complexity, where n is the data point, k is the cluster, and t is the iteration. So generally scalable. So K means scalability. K means handles large data set efficiently with O of nkt complexity, making it deal for production systems processing millions of customer records. So companies like Amazon and Flipkart use K-means to cluster millions of customers daily for recommendation and marketing. Okay, so when choosing a clustering algorithm for a real project, always consider how big is the data set. How fast does the algorithm need to run? Does it need to run daily or just once? So these questions help you pick the right algorithm. Next, algorithm usability with multiple data types. See, in the real world, data sets rarely contain just one type of data. A hospital record might have a patient's age, that is numeric, diagnosis, it is nominal, test result, it will be ordinal, and insurance status, it will be binary, right? So all in a single record. Now in single patient's record, you will have age as numeric data type, diagnosis as nominal, test result as ordinal, and insurance status as binary. So a robust clustering algorithm must be able to handle this diversity. So a type of data, a good algorithm must support all the things, whatever we have seen: numerical data, categorical data, binary data, and mixed attributes. So numeric in the sense age, income, temperature, height, etc. Categorical, color, gender, country, blood group. Binary, always two values. Yes, no. True, false. Infected, not infected. Mixed attribute means a single data set containing all of the above. That is mixed. Okay, K-medoids, an algorithm that handles mixed data. K-medoids. So unlike K-means will compute the average or mean of a cluster, which does not make sense for categorical or binary data. But K-medoids uses an actual data point as a cluster center called a medoid. This makes it compatible with any distance measure, Manhattan distance, Jaccard similarity, or customer metrics. It can handle any data type as long as you define a similarity or distance function. So what is the major difference between K-means versus K-medoid? K-means means center, average of all points in clusters. Works only for numeric data. K-medoid, center, the actual data point closest to all other in the cluster. Works for any data type. Example, if you cluster people by age, blood group, income, K-means can't average blood groups, right? But K-medoid picks a real person as the representative. So in ADS, you will often receive messy real-world data set with mixed types. Knowing which algorithm handles which data type will help you choose the right tool for every project. Handling unstructured data. So far, we have discussed structured data. That means data that fits neatly into rows and columns like an Excel sheet. But in the real world, most data is unstructured. It does not have a predefined format. Modern clustering algorithms are powerful enough to handle this. Okay, what are the types? Types of unstructured data clustering. Text documents, images, audio files, social media data. Text document. See, clustering algorithms can group articles, customer reviews, or emails by topic. Okay, this all will come under text document. For example, grouping news articles like into politics, sports, entertainment, and technology. Categories without manually labeling each one. Okay, images. Algorithms can segment objects in images or identify visually similar pattern. Used in medical imaging like grouping similar X-rays, satellite imagery analysis, and face recognition systems. Audio files. Next type of unstructured data is audio files, detecting speaker changes in a recorded call. Speaker diarization, classifying the music into genres or identifying similar sound patterns. Okay, next one, social media data. Organizing social media posts by trending topics, then clustering Twitter, Instagram users by behavior, or identifying viral content patterns. So I can give you one same example. I take the same Netflix. Netflix uses clustering to group movies by genre, mood, and viewer preferences. This is done using unstructured review text, what viewers write about a movie. Okay, that is the review. And viewing patterns, how long they watch, what they skip. So this is viewing pattern. None of this comes neatly labeled in a spreadsheet. Okay, so flow. Let me say the flow of this topic. Unstructured data, feature extraction, convert to numbers or vectors, clustering algorithm, then organized groups. So the key challenge with unstructured data is converting it into a form that the algorithm can measure distance on. Interoperability in clustering. Interoperability means the ability of a clustering system to work seamlessly with various data sources, platforms, and tools. In enterprise and production environments, data does not sit in just one place. It might be spread across databases, cloud storage, APIs, and file systems. So what interoperability clustering system can do? They can work with multiple data sources. They can read from SQL database, NoSQL database, MongoDB, CSV file, Excel sheets and more. Integrated with different platforms. That means they can connect with platforms like Hadoop, Spark, AWS, Google, Cloud. Support various database systems compatible with MySQL, PostgreSQL, Oracle, MongoDB, Cassandra, etc. So enables real-time analytics. It can process live streaming data from IoT sensor, financial markets and cluster it in real time. So what is the benefit of this interoperability? So data sharing across system. That means multiple teams can use the same clustering result. Integration with analytical tools. Export the clusters to tools like Tableau, Power BI or Python for further analysis. Scalable data mining workflows. Works within large enterprise data pipelines. Enterprise level deployments suitable for production use in large organizations. So I can give you one real world example so that you can easily understand. A bank's fraud detection system. It reads customer transaction data from a SQL database, real-time card swipe data from API, and historical data from cloud storage. All of these are fed into a clustering system that identifies unusual transaction clusters in real time. This is only possible because the clustering system is interoperable. Okay, so as an AI designer, you won't always work in isolation environments. You will need tools that can talk to each other. Always evaluate. Can this algorithm integrate with our existing data pipeline? Think. Types of clustering methods. So clustering techniques are not one size fits all. Different types of data and different problem scenarios require different approaches. So there are 4 main categories of clustering methods. First one is partitioning method. Second is hierarchical. Third is density based, and fourth one is grid based. So partition means the data set is divided into non-overlapping groups, that is partitions, and it is represented by a letter called K, that is constant. Okay. Each data point belongs to exactly one cluster. Each data point, one cluster. The algorithm iteratively reassigns points to cluster to optimize a criterion, usually minimizing the distance. So example, K means and K methods. And where it will be used means it is simple for numerical data. It is used like it is best for compact spherical clusters of similar size. Okay. Next one is hierarchical. So it creates a tree-like structure of clusters called a dendrogram. Dendrogram is nothing but a tree-like structure. So in this 2 approaches are there. One is agglomerative, that is bottom up, and another one is divisive. Okay. So agglomerative bottom up means it starts with each point as its own cluster, merge the closest pair step by step. But divisive, that is top down. It starts with all points in one cluster. Recursively it will split. Okay. So best where it will suit means when you don't know the number of clusters in advance, you can go for this method. It produces a visual tree that shows relationships at different levels. So the tree name is what? Tree-like structure is dendrogram. Okay, third method is density based method. See, clusters are defined as dense regions of data points. Dense region. So separated by regions of lower density. So can find clusters of any shape, not just spherical, automatically identifies and ignores noise. Example, DBScan. That is density based spatial clustering of applications with noise. That is DBScan. DB, density based. SCAN, spatial clustering of applications with noise. So it is best for datasets with irregular shaped clusters and noise or outlier points, commonly used in anomaly detection and geospatial data. Okay, and the last method is grid-based method. So the data space is divided into a grid of cells. Clustering is done on the grid cell rather than individual data points. Very fast. The processing time depends on grid size, not the number of data points. Example, sting, click, and especially it is best for very large data set where speed is critical. So it works well with spatial data. Okay. So comparison. Partition means what? Fixed K, spherical clusters. Then next is hierarchical, tree structure, any K. Density based, any shape, handles noise. And last one, grid based, means very fast spatial data. So in your exams and interviews, you will often be asked which method would you choose for a given scenario. So use this comparison to ask confidentially. Okay. So we have come to the end. The remaining portion we'll cover in the next part, that is part 2. So now I'll give a quick recap. So this slide serves as a recap and a bridge to connect with what we have learned today with the broader picture of data mining techniques. So let's take a moment to consolidate everything covered in this session. What we covered today, cluster analysis, a data mining technique that groups similar objects automatically without predefined labels. Why do we need cluster analysis? To discover the patterns, to organize data, to find natural groupings and support decisions. So what are the different types of data? Interval scaled, binary, nominal, ordinal, ratio, each handled differently. Next we have seen about properties of good clusters. So in that, high intra-cluster similarity, low inter-cluster similarity, computational efficiency and scalability. So scalability means the algorithms must handle large data efficiently. So K means O with O of NKT is a strong example. Multiple data types. So K-medoids handles mixed data types, usually using actual data points as centers. And next we have seen about unstructured data. So like text, images, audio and social media. These all can be clustered. And next is interoperability. Clustering systems must integrate with diverse data sources and platforms. And last we have seen about the types of clustering methods. There are 4 methods: partitioning, hierarchical, density based and grid based. So clustering is one of the 3 main tasks in data mining alongside association rule mining and classification. Okay. So unlike classification, clustering has no predefined categories. It discovers them from the data itself, making it a powerful tool for exploratory data analysis. So in the next session, we'll dive into the algorithms in detail. How does K-means work step by step? What is a dendrogram in hierarchical clustering? And how does DBScan identify noise points? So be ready. We'll just, you can ask the questions like what is cluster analysis and how it is different from classification? What are the properties of a good cluster? And what are the different types of data used in cluster analysis? And why is scalability important in clustering? And you can compare partitioning and hierarchy. And what is interoperability? So ask these questions to yourself, and if you can able to find the answer, means hope this video was helpful to you. Okay, thank you. Thanks for watching. We'll catch up in the next video.